Okay, we have just finished step growth polymerization. So let's begin addition or chain growth polymerization. So in this chain growth polymerization part, we'll learn about these three different types of addition polymerization method, including free radical polymerization, anionic polymerization, and also cationic polymerization. So let's first begin with free radical polymerization, at which free radicals are involved in the polymerization process. So as you recall from step growth polymerization, mostly monomers with two functional groups reacted with each other, right, in forming long chain polymers. But there are big differences between free radical addition polymerization and step growth polymerization. Some of them are described here. First, free radical addition polymerization occurs by three different steps, including initiation, propagation, termination. So we learn about each of these processes in the following section. So as you recall, in step growth polymerization, there were not like these kind of steps, right? Monomers with different functionalities, such as like hydroxyl group and carboxyl group, just reacted with each other, right? By the condensation reaction. So it's quite different. Secondly, in free radical addition polymerization, monomer molecules are added to a growing chain. So there is a certain growing chain, and monomer are added one by one. Okay? But in step growth polymerization, as I just mentioned, any molecules had two or more than two functional groups. So they could react with each other, forming longer chains, right? Monomer, dimer, trimer, any molecules inside of the reaction vessel could react with each other because they all had functional groups. But in free radical polymerization, only growing chain which contains free radical, actually, to this growing chain, monomer molecule can be attached, can be added. Okay? That's why we call it addition polymerization. Okay? So here, monomers generally have this kind of form. As you remember, this kind of a kind of vinyl polymer, right, with double bond. This is the monomer. So this double bond is susceptible to free radical attack. Okay? So let's say we have the free radical and we have monomer here. Okay, so attacked by monomer and by the free radical and just forming a little bit one monomer longer chain. Third feature of free radical polymerization is long chains are present at an early stage in the reaction. If you recall, in step growth polymerization, if you recall Carnot's equation, we needed high conversion to achieve high molecular weight or long chains, right? Which means that also we need long reaction time. But in free radical polymerization, we have free radical. And if you recall from organic chemistry class, free radicals are really reactive, highly reactive species. So they can attack monomers really quickly, one by one, at a much short time. So even at an early stage, even after a short time after beginning the reaction, we can achieve high molecular weight, something like this. very high molecular weight at very short time. Okay. Fourth feature is unreacted monomer are present until the end of the reaction. So we just said that only growing chain with free radical can attack monomer molecules. So any monomer molecules which were not attacked by this free radical can survive until the end of the reaction. Okay, that's quite different from step growth polymerization, right? In step growth polymerization, monomers they all have functional groups, so they can just react with each other with the neighboring molecules, right? But in free radical polymerization, only free radical can attack monomers. Okay, so it seems that these two different polymerization methods are quite different. So let's see more about more details about these free radical addition polymerization. So let's move on to the next page. So here shows you the common monomers, common polymers synthesized using free radical addition polymerization. As I mentioned, many of vinyl polymers, these are vinyl groups, right? Vinyl polymers are made using free radical polymerization, forming this kind of polymer. Okay, so we could have different Y functional groups. It could just alkyl chain or benzene. If it is benzene, what is that? It is polystyrene, right? If it is halogen, such as it is chlorine, that is PVC, right? Polyacrylonitrile or some other polymers. Okay, so mostly vinyl monomer can vinyl polymers are generally synthesized using this free radical addition polymerization. Okay, so let's first begin with initiation process. So in previous slide we saw that there are three different steps, right? Initiation, propagation, and termination in free radical polymerization. So let's first start with the initiation process. So initiation. So we learned from organic chemistry class that free radical, above free radical. So free radicals basically contains unpaired electron, so they are extremely reactive. Okay. Then how can you form free radical in reaction, in chemical reaction? How can you make free radical? There are mainly two different ways to make free radical. The first way is called homolytic decomposition, at which a certain compound are decomposed into same two radicals. And the second method is electron transfer from ions, basically redox reaction. So let's see one by one. So homolytic decompositions are described here. So basically homolytic decomposition means that a certain covalent bond inside the molecules are just broken into a same two molecules. Okay, the breaking of those covalent bonds can be performed by a certain kind of energy. It could be thermal. You can just heat it up, or you can just shine some light, etc. Anyhow, we need some energy. So effective initiator should have these kind of characteristics, such as it should be easily broken down to a radical, which means that covalent bond, the bond strength should be small, about this range. So covalent bond with this kind of relatively small bond strength include oxygen-oxygen single bond, nitrogen-nitrogen double bond, ON single bond, or SS single bond. Furthermore, that compound should be stable long enough to react with monomer and form active center, which means that after you form radicals, we learned that radicals are extremely reactive. Since they are extremely reactive, they could just react with each other and form a non-radical compound immediately, right? It's a possibility. But what we want is we want to use the radical to make polymers, right? To do that, we need to generate reactive radicals, but they should maintain at least for a certain amount of time to proceed the remaining polymerization steps, right? So on example of the initiator, the representative example is benzoyl peroxide. The benzoyl peroxide looks like this. As you see, it's totally symmetric molecule, right? So if you, for example, heat it up, you can break this bond and basically forming 2 moles of the benzoyl radicals. And after removing CO2, you can form basically 2 phenyl radicals. It only requires about 60 degrees C at benzene solution. Relatively small amount of heat thermal energy, right? But there are some things that we need to consider. Radicals formed are not 100% efficient. So by simply heating up the initiator molecules, we can make radicals, but the generation of the radicals are not 100% efficient, which means that there are 2 different cases. The first case is called cage recombination. So we form 2 molecules of 2 radical molecules, but if you perform the reaction inside of the solution in the liquid phase, these radicals could be surrounded by solvent molecules. But what we want these radicals to react with monomer, right? By doing that, we can make long chain polymers. But if these 2 radicals are surrounded, kind of caged by solvent molecules, then they would just react with each other, basically forming the initiator again. They kind of just die, right? It could happen. Another example is called induced decomposition. So we made radical from BPO. Since it is really reactive, it can react with the initiator BPO molecule, okay? Basically forming this and another radical. Okay? From this one initiator, ideally, we could make 2 radicals, right? From one BPO, we could make 2 radicals. But here, we have 1 initiator, but could only make 1 radical. It's kind of waste, right? It's waste of initiator, right? So because of these 2 mechanisms, radicals are not 100% efficient. So we need to consider the efficiency of radicals. So this is an example of the initiator. Another example of the representative initiator is azo compound. So azo means basically nitrogen double bond. Okay? So the composition of the azo compound can generally performed by heat and also by light. So as you see, this molecule is called azo-bis isobutylonitrile, or abbreviated as AIBN, which looks like this, which is also symmetry molecules. Okay, so if you usually shine light, okay, for example, like the ultraviolet light, then you basically break this bond, forming two moles of this radical and nitrogen gas. Okay. And generally, compared to this thermal decomposition, this photolytic decomposition, okay, by using light, much more favorable, more selective, and we don't really need to heat it up. We can just form at room temperature, and radical generation can be stopped, because I mean radical generations are basically controlled by the shining light, right? So we can, if you just stop shining light, then you can just stop the radical generation. Another method is by redox reaction. For example, if you have peroxide, if you react it with the ferrous ion with 2 plus ion, okay, then this ferrous ion can be oxidized to ferric ion, basically giving up 1 electrons to peroxide. Then peroxide have additional electrons, and it can generate radicals. Okay. But I mean, in general, free radical addition polymerization reaction, we usually use azo compound or BPO compound. So these redox reactions are hardly performed compared to other methods. Okay. So by initiation process, we formed radicals from initiator molecules, right? After that, we just have radicals, okay? After that, this radical, which is highly reactive, react with monomer and form something called active center. So here, active center is just radical, free radical, but there's only one monomer attached to it. Okay. There are two possibilities. Let's say that monomer is just this vinyl compound. Radical is reacted with this vinyl compound. It could react to this side or to this side. Okay, so two different products are possible. Okay, but in reality, this is more probable. The reason why is that if this X group, these X side groups are bulky, okay, because of the static hindrance, okay, basically reacting this side is not, I mean, is possible, but relatively small amount of these radicals are formed, okay, because of the high activation energy, because of this static hindrance. Okay. All right. So this is the initiation process: formation of radical and formation of active center. Okay. All right. And then there is propagation process. Propagation means basically making longer chains, right? So this, in propagation process, this active center react with monomer. Okay, it just attacks monomer molecules and it form dimeric radicals, right? And these dimeric radicals react with monomers, and they form RM3 dot, and this RM3 react with monomer and forming RM4, right? So since radicals are highly reactive, this process occurs quite quickly. Okay, so generally, propagation step can be written in this way. Okay, radical react with monomer, forming another radical with a little bit longer chain. Okay. So as I mentioned, since radicals are highly reactive, the average lifetime of the growing chain is really short. Okay, it only takes a few seconds to form several thousand additions. which means why we could achieve really high molecular weight, really long chain polymers at an early stage of the reaction in free radical polymerization. Okay, so similar to this, initiation process, this propagation can also occur in two different ways. It can form this kind of head to tail addition, or head to head addition, something like this. Okay, similarly to the previous discussion, this is more favorable, right? Because of the steric hindrance between these two bulky side groups. Okay, and finally we have termination process. Termination process. So termination means radicals basically die. Okay? So radicals react with each other, basically form inert or non-reactive polymers. So generally there are two different mechanisms. Actually there are three, but here only shows two main termination mechanisms, which are combination and disproportionation. So as the name indicates, combination or coupling means two long chain radicals react with each other, forming longer chain. Okay, so basically from two growing chains, we basically form one chain, and the length of the resulting chain would be the sum of these two growing chains, right? On the other hand, disproportionation, we have two of these growing chains, and they just die, but they do not just connect with each other. Okay, just forming two dead chains. Okay, I didn't really mention about the rate constant of each process: initiation, propagation, and termination. So let's go back. I mean, we'll cover this kinetics part soon, but let's briefly talk about the rate constant. For initiation process, the rate constant is on the order of this 10 to minus 4 to 10 to minus 6. Oh, this is not really fast. For propagation process, the rate constant is 10 to 2 to 10 to 4. It's faster, okay, much faster actually than stack cross polymerization. If you see the rate constant, the termination, sum of the combination and disproportionation rate constant is 10 to 6 to 8. It's much larger than propagation process. Okay, it's quite weird, right? If the rate constant of termination process is larger, much larger than propagation step, then we cannot really make long chain polymers, right? How can you make polymers? Okay. So to understand this, we need to consider the overall reaction rate, which will be covered soon later. Okay. Okay. So I just skip this part, and we just have seen that there are two main termination mechanisms, right? Combination and disproportionation. Another mechanism is called chain transfer. Okay. Chain transfer is basically as the name indicates, the radicals are transferred to another species. For example, let's say that we have growing chain with radicals. It can react with any species, including monomer, polymer, solvent, or some other chain transfer agent. And these radicals are just transferred to these species, and these growing chains just die. Okay, they are just dead chains. Okay, and from this radical, it can start another polymerization process. Okay, all right. So if we experience more chain transfer, then they will tend to reduce overall average molecular weight. Okay, So up to here we briefly introduced what free radical addition polymerization is and the overall three different steps: initiation, propagation, termination. Okay. Okay. Let's now start the kinetics of free radical addition polymerization. So we have learned that in free radical addition polymerization, there are three different steps, right? Initiation, propagation, and termination. So we want to see the more details about the kinetics. We briefly compare the rate constant of each step, but we didn't really write the rate law, right? So let's write it down. So let's first consider the initiation step. So we have seen that in the initiation step there are two reactions, right? The first reaction, the initiator forms two moles of radicals. Okay? And this first reaction is relatively slow. So overall, among these two steps, the first reaction is the RDS or rate determining step. So the rate constant is Ki, okay, in the first reaction. And as a second reaction, the radical react with monomer forming active center. Right, this is fast. Okay, and the rate constant is denoted as Kr. And here, the amount of monomer consumed during the formation of active center is negligible, right? Because in reality, initiation step also consumes a small amount of monomers, but we could just neglect it because the amount of monomers consumed during propagation steps are much larger, right? So anyhow, among these two reactions, since the first reaction is rate determining step, we can write the reaction rate for the first reaction. So overall, the initiation process, the rate can be written in this way, right? The change of the concentration of the initiator as a function of time, which should be same as this, right? Concentration change of the radical concentration, the product of the first reaction divided by the time. We have to put 2 here, right? Because we are forming 2 moles of radicals from 1 mole of initiator, which should be equal to Ki times I, right? Okay. But this equation is valid only when the initiator is 100% efficient. Okay. So in previous lecture, we learned that because of cage recombination and also some other non-100% efficient process occurring in the reaction media, there is only a certain portion of the initiator used, right? So we'll just put F here. F is the efficiency of the initiator, which should be between 0 and 1, right? So anyhow, this is the reaction rate for the initiation process. Okay, next is propagation. So as you recall, propagation is basically the reaction between the growing chain with the radical with the monomer, so forming a longer chain. So here Kp is the rate constant of the propagation process. So we'll assume that the Kp is just constant, independent of the length of the growing chains, right? So if the Kp is different depending on the polymer length, then that would make the problem really complicated. So, and in reality, the reactivity of the free radicals are really high, as we can easily assume that that reactivity is similar, independent of the polymer chain. So if you write the propagation rate, that should be the change of the monomer concentration as a function of time, since monomer is the reactant, we should put minus sign here. Okay, and the rate should be equal to Kp times the first reaction, second reaction, third reaction, etc. Okay, and you can just cut some of these terms and forming something like this. Okay, so since it is not really convenient to write this sigma, so from here we'll just write it in this way: Kp times m times just m dot. Okay, let's just just try to understand this is just m dot. Okay, to make it simpler. Okay. All right. So this propagation step is the major step, right? At which the long chain polymers are formed. So the rate of propagation is actually the rate of polymerization in this free radical polymerization process, right? But the problem is here we need to know the concentration of the radicals inside of the reactor, right? But as shown here, radical concentration is very difficult to measure, and also in the reaction of during this free radical polymerization, the radical concentration is really low. I mean, there is a experimental method to measure radical. It's not really common, but there is. But since the concentration is really low, it's really hard to measure. So it's really impractical using this term to express the propagation rate or the overall polymerization rate. So we need to eliminate this term and replace it with other terms. Okay, just let's keep this in mind. Okay, and let's move on to the termination step. Termination. As you recall, termination steps, there are two different mechanisms: combination and disproportionation. Okay, so two growing chain radicals just forming longer chain or just die by themselves. Okay, with KTC is the rate constant for the combination step. KTD is the disproportionation step. Okay. So if you write the termination rate, you can write it this way. Okay, this way or this way. So since we basically kill two radicals by this each of these termination steps, we have to put 2 here. Okay. And let's just denote this KT as the sum of KTC and KTD. Okay. And also, since the sum of the radical concentrations should be same, right? So we can easily just rearrange these into these expressions. Okay. So, as I just mentioned in previous slide, we'll just write this part as just m dot. Okay. All right. So in previous slide, we wanted to eliminate this radical concentration term, right? It's not really practical. So to do that, we'll use steady state approximation, which means that the radical concentration is relatively constant during the process of the reaction. Actually, in reality, it is experimentally verified by this ESR, electron spin resonance experiment. Okay? So it's not really vague assumption. It's a fairly valid approximation. Okay, you can actually see the overall. This is not really. I didn't really put it here, but anyhow, experimentally, it is a relatively valid approximation. The concentration of the radicals constant during the reaction. So since this is constant, if you take the derivative, it should be 0. Okay? Which means that since the concentration of the radicals are constant, the generation of the radicals and the termination of the radicals, the rate of each should be same. right? Basically, the initiation rate and the termination rate should be same. Okay, so from previous initiation rate and the termination rate, if you use, where is it? This term, sorry, this term and this term, okay, if they are same, then you can just have this expression. Okay. Okay, then the overall reaction rate of the free radical polymerization, which is propagation rate, okay, then we can just put this radical term, this part into here. Okay, then we could easily obtain the propagation rate or the rate of polymerization in free radical polymerization as shown here. Very important result. Okay, so as you see, the overall polymerization rate in free radical polymerization, these are just constants, right? It is proportional to the monomer concentration and also root of the initiator concentration. Okay, and usually we use very small amount of initiator, then this part is also almost constant, then the overall propagation rate, polymerization rate is just the first order rate, follows first order rate law, right, for the monomer. Okay. So as you see in this picture, this shows the time reaction rate versus time. So as you see in this free radical addition polymerization, there's an initiation process and the termination process, and during the most of the time it forms relatively constant reaction rate at which initiation and termination rates are same. Okay. Alright, so let's move on to the molecular weight part. If you recall from step growth polymerization, we learned about degree of polymerization, right? Number average degree of polymerization, remember, right? It basically means the in average how many monomers are connected with each other, right? Similarly, in free radical polymerization, we use the term called kinetic chain length nu. So the definition of kinetic chain length is average number of monomer molecules added to each radical during its lifetime. So it's kind of similar meaning to the that of degree of polymerization, right? So basically, how many monomers are attached, added to a radical. So this kinetic chain length can easily be calculated by dividing Rp by Ri, right? Because Rp is the propagation rate and Ri is the initiation rate. How many monomers are attached per radical generation, okay? And from steady state approximation, this Ri is equal to Rt, right? So you can put the Rp here and Rt here, okay? Then you basically have these expressions, okay? Then by using the expressions for m dot that we obtained here, this one, okay, this equation 7, we can put that equation 7 into here, then you can get these expressions. Okay. Okay. So the kinetic chain length in free radical polymerization, so the other parts are basically constant. It is proportional to the monomer concentration and inversely proportional to the root of the initiator concentration. So it's much more complicated to the step cross polymerization, the Kerdos equation, right? 1 over 1 minus p. Okay. So if you want to determine the degree of polymerization in kinetic chain length, it could depend on the termination mechanism, right? If you form polymer chains by termination mainly by combination, and by combination you form much longer chains, right? Because we combine two free radical chains, right? So the degree of polymerization is equal to 2 times kinetic chain length. But if the termination mechanism is mainly disproportionation, then degree of polymerization is equal to kinetic chain length. Okay. So generally, it should be in between, right? It should be in between. Okay. So we have already learned about chain transfer, so I'll just skip this part. Oh, sorry. So we learned about this chain transfer, right, before, right? Remember, right? Chain transfer is basically the reaction between the free radical with some species, right? It could be anything, right? Monomer, initiator, solvent, and polymer, right? So if there is a termination process occurring by chain transfer, we should also consider that. So reaction between the radical with the chain transfer agent, and the rate constant is KTR. Okay? So if you consider this, let's say that we want to consider chain transfer to monomer, initiator, and solvent separately. Okay? Then that each of these chain transfer reaction, we can write the rate law, right, this way. So the chain transfer to monomer, KTRM, should be equal to reaction between radical and monomer, right? To initiator should be equal to radical initiator. To solvent should be equal to radical solvent, right? Same, quite similar. Okay. Okay. So if you calculate the kinetic chain length when considering chain transfer, so by definition, kinetic chain length is Rp over Ri, right? Or Rp over Rt, right? Okay. So Rp is basically same, right? Propagation rate. Okay. And Rt should be combination and disproportionation and chain transfer, right? Okay. And if you consider the disproportionation only, okay, then Xn degree of polymerization should be equal to kinetic chain length. And if you take the reciprocal on both sides, okay, if you take the reciprocal like this, 1 over Xn should be equal to, if you take the upside down, something like this, right? Okay. So here, there are some constant here, C. So C is defined as the KTR X over KP, basically the ratio between the chain transfer rate constant to the propagation rate constant. Okay. So this part is the 1 over Xn 0 when we do not consider chain transfer, right? So let's say that we use some compounds as chain transfer agent. Okay? Then it could be monomer, initiator, or solvent. Let's say that it's solvent. Okay? And you just vary the solvent concentration. Okay? And if you can, after you finish the polymerization process, you can determine by experimental method, you can determine the degree of polymerization or the molecular weight of the polymers, right? So you can experimentally plot 1 over Xn versus the concentration ratio of the solvent and monomer, shown here. Okay? So from this experimental data, from the slope of this data, something like this, we can determine this transfer constant of the solvent, or it could be Ci if you vary the initiator concentration, something like that, right? So here shows an example. The chain transfer can also occur to not just initiator solvent monomer. It could also happen to polymer. Okay, if you react to the if the reaction occurs between the free radical to polymers, then this polymer can obtain this free radical. Then additional branch could happen. Okay, or another example is called backbiting. Okay, so here is the chain with the free radical, and this radical can, I mean, it should react with the monomer, but it could just react with the a part inside of this chain. Okay, so this is also possible, and if this happens, if this chain transfer to polymer, or if this backbiting happens, then branches can form. Okay, basically resulting in lower crystallinity of the polymers. Okay, previously in free radical addition polymerization, we have learned about the kinetics. Okay, so we have run the rate law for each step: initiation, propagation, and termination. And based on steady state approximation, we could obtain the overall polymerization rate, which is propagation rate, okay, in terms of monomer concentration and also initiator concentration. And also we have learned about the kinetic chain length. And today, the title of today's talk is auto acceleration, or also denoted as gel effect, Tromsdorff-Norrish effect. Okay, so we could assume that we could use the steady state approximation at which the generation and the termination of the radical is basically the rate is basically same, right? And also we learned that assumption is valid, and it was checked experimentally. But this auto acceleration shows that could have some deviations from this steady state kinetics during free radical addition polymerization. Then when does this happen? When does this auto acceleration happen? Especially when toward the end of reaction, using pure monomer, high concentration of monomer, and basically high concentration of monomer. Okay, so let's see why. So we have learned that basically the rate of the polymerization should follow this equation, right? The change of the basically the decrease in the amount of monomer concentration as a function of time is proportional to the monomer concentration. You remember this, right? This is the first order kinetics, and if you integrate it, you can have these relations from this. Okay? It's quite obvious, but in reality, this is the picture from the textbook. If you look at the log m0 over m, this part, which in theory should be proportional to the time t, reaction time. Okay, so it is proportional at the beginning of the time, reaction time, but as the reaction time lasts towards the end of the reaction, this value suddenly shows this kind of increase, sudden increase, especially when this number is the concentration of the monomer inside of the reactants. When the concentration is really high, 80%, 60%, or even 40%, it shows huge deviation from this theoretical relation between this log m0/m and time, reaction time. Okay? The reason why is very simple. The reason why is increase in viscosity of the reaction medium. So what does this mean? As the reaction proceeds, we are basically generating long chain polymers, right? And long chain polymers have higher viscosity compared to monomer molecules, right? And especially in the case when you use really high concentration on monomer, right? Then the increase in viscosity will be huge. Okay. And the problem is, if the viscosity is increased, which means that the polymer chains are much harder to move inside of the reaction medium, right? Then the rate of termination decreases, right? Because if you want to make the polymer chains just die by termination, then they should meet with each other, right? But because of this high viscosity, they cannot really meet. Okay? But the initiation and propagation take place at roughly the same rate. Okay? The reason why is that monomers are much smaller than polymer chains, right? Long polymer chains. So although initiation propagation proceeds at a similar rate, but the termination hardly occurs. Okay? But the problem is this polymerization process, especially the propagation process, is exothermic. So we really need to just dissipate. We need to remove this generated heat. Okay? If we cannot remove this heat, then we might have some problems such as like explosion because of this high heat. Okay? So it could be very dangerous to use this kind of high concentration monomers. Okay? Especially at the end of the reaction, it might just break the reaction vessel from explosion. So to make this gel or auto acceleration and to prevent this auto acceleration from happening, we need to use not high concentration. We need to use like dilute solutions, or we can just stop the reaction at relatively low conversion. Okay, so because it could be very dangerous. Okay, so this is auto acceleration, and in this free radical addition polymerization, we have learned that these free radicals are extremely reactive. Right? So if you just start the reaction, it happens really fast, right? Okay. So generally, for example, if you buy these monomer molecules from some commercial vendor, there is some materials inside of this monomer bottle, which is either inhibitor or retarder, which are the chemical species that basically slow down or stop the radical, the reaction. So retarders basically act as slows down the polymerization rate, and inhibitors are used to stop the polymerization reaction, basically stop the free radical. The mechanism is very simple. The representative retarder that are used are mercaptan, which has the SH group. Basically, if there is a radical, okay, this mercaptan react with this radical and take this. Sorry, this one just gives one radical to the monomer. Okay, basically removing this radical, and this mercaptan becomes radical. Okay, basically making the monomers unreactive. Okay, and this uh, uh, S radical is much more stable compared to this monomer radical. Okay, basically, sorry, the mechanism is shown here. Okay, as I mentioned before, just before. Okay. Either inhibitor or retarder, Z, basically they become radicals, which is much stable compared to the monomer radical or the molecular radical, and these molecules become non-radical species. Okay, so generally, if you buy these monomers, for example, if you want to make, let's say, polystyrene, you need styrene as a monomer, right? If you buy from some chemical vendor, there's always this retarder or inhibitor materials inside, small amount inside of the bottle, because by chance, if you just hit the bottle, or just if you like shine light to the monomer bottle, it might just start the synthesis, the chemical reactions. So to prevent that, usually retarder or inhibitor molecules are contained inside of the monomer bottle. Another retarder or inhibitor molecules include nitroaromatics, so retarder, or benzoquinone or antiroquinones are also commonly used. For example, this benzoquinone also has this one, also has this form. Okay, you can readily react with radical species. Okay, basically generating non-radical, the hydrogen added species, and they become this stable benzoquinone. Alright, let's move on to the effect of temperature in free radical polymerization. So, we learned that there are 3 steps in free radical addition polymerization: initiation, propagation, termination. And each step, there were rate law, right? Remember? So, for initiation, the rate constant was Ki. For propagation, Kp. For termination, Kt. And as you learn from general chemistry class or reaction engineering class, that this rate constant follows Arrhenius equation. So pre-exponential factor times exponential minus activation energy over RT, right? So for each of these rate constant, there should be activation energy for initiation, activation energy for propagation, and termination. Okay. And if you recall the propagation rate of polymerization, this rate of polymerization that we have derived before was this expression, remember, right? So if you put these 3 rate constant into here, okay, then you get these expressions, how the rate of polymerization depends upon the temperature. Okay, so it should be depend on the activation energy of each step, right? Termination, initiation, and propagation. And generally, in free radical polymerization, the initiation activation energy is in between 120 and 150 kilojoule per mole, propagation 20 to 40, termination 8 to 20. Okay, so let's put these numbers inside of here. Okay, let's say that EI is like 130, EP is like 30, ET is, let's say, just 10 to make a simple calculation. Okay, if you put it here, this one here, okay, then the calculated value, this one, is negative. Okay, which means that this rate of polymerization, as the temperature increases, this rate of polymerization also increases, right? Okay. Similarly, if you remember the degree of polymerization or the kinetic chain length for the free radical polymerization, you follow this equation, right? And if you put the Arrhenius equation into these three rate constants, then you basically get this temperature dependence of number average degree of polymerization in free radical polymerization. And if you also calculate this value based on these numbers, then the resulting value is actually positive, which means that as you increase the temperature in free radical polymerization, the average degree of polymerization, or average just polymer chain length, actually decreases. It's quite interesting, right? As you increase the temperature, the rate increases. That's kind of general phenomenon, right? But as you increase the temperature, the average chain length decreases. Okay. For photo-initiated polymerization, when you use the initiator, which is basically, for example, like azobenzene, then the activation energy for initiation is 0. Okay. Then if you put those numbers of the activation energy here, EI is 0 and EP is, for example, 30, ET is like 10. Okay. Then you can get that for photo-initiated free radical polymerization reaction, as you increase the temperature, both rate of polymerization and the average chain length also increases. Okay, that's the difference between the thermally activated polymerization and also photo-initiated polymerization. Okay, so since you have learned that as you increase the temperature, the average chain length decreases. Okay, so from this knowledge, that we had to consider the sealing temperature, Tc. So if you consider the propagation, let's say that this radical react with monomer and forming the longer chain. Okay. In this reaction, actually, we should consider the forward reaction and also reverse reaction, because this reaction is reversible. It could be reversible, right? So we have to consider polymerization and depolymerization equilibria. Okay. So if you denote the rate constant of the forward reaction as Kp, rate constants of the reverse reaction or the depolymerization reaction as Kdp, then we should consider both forward and reverse reaction. Okay, and when you consider this reversible reaction, and if you write the rate reaction rate, okay, reaction rate, then you can just write it in this way, right? For the reaction and the reverse reaction. Okay. And if you consider a steady state condition, then this one should be 0. Then you can get this relation, this relation. Okay. So which means that depending on the temperature, at a boundary between a certain temperature, which is denoted as ceiling temperature here. For instance, like below this ceiling temperature, the forward reaction will be more favorable. On the other hand, above the ceiling temperature, the reverse reaction will be more favorable, right? And at equilibrium or at steady state, these two values are the same, as shown in this picture, right? Okay, so which means that below this temperature, this forward reaction part is larger than reverse reaction part, but here above Tc, the reverse reaction is larger than the forward reaction. Okay, which means that this ceiling temperature is the temperature at which we could get the longest polymer chains, right? Because above this temperature, we cannot really make this propagation happen, right? The reverse reaction is more favorable above this temperature, right? Okay, that's why we call it ceiling temperature. The ceiling is the upper bound of the room, right? Okay. Next is determination of individual rate constant. So we have seen that there are three rate constants, right? Ki, Kp, and Kt. Okay. To determine each of these values, since there are three variables, we basically need three equations, right, to determine all of these values. So generally, there should be some terms which can be experimentally determined, and we need three of them, right? So let's see just briefly how we can do it just in qualitative manner. Okay, first, we could use radioactively labeled initiator and determine the mechanism of termination. So remember, if you remember the relation between the average degree of polymerization and the kinetic chain length, okay, they are basically proportional to each other, right? If it's like combination only this A value is 2, if it is disproportionation only A is 1, right? And if you remember the rate of propagation and also the average degree of polymerization, in these equations, you can basically change the monomer concentration and initial concentration, right? That's to be just measure when you start the reaction, and also we can easily determine the average degree of polymerization by checking the molecular weight of the resulting polymers. Okay. So by where is it? So from this equation, these two equations, as you see, these two, I mean, we can also easily check the reaction rate, right? So from these two equations, the dependence of these two propagation rate and the average degree of polymerization basically follows Kp times Ky root Ki over root Kt. Here, Kp over root Ki and root Kt, right? So dependence of this initiation rate constant is different, right? So by doing different experiments, we can easily determine the Ki, but the problem is dependence of both of these propagation rate and the degree, number average degree of polymerization on Kp and Kt are same, right? Kp over root Kt, Kp over root Kt, right? Because they basically have the same dependence. Okay, so we need additional experiment, right? So for that, what people usually measure is average lifetime of growing chain. Okay, so definition of this average lifetime of growing chain, denoted as tau, is concentration of growing chains at any time over rate of disappearance of growing chain. So which I'm not going to go into the details about how we measure this, but just assume that just we can measure this tau value experimentally, okay? And this value basically have this dependence upon the rate constant Ki and Kt. Okay, so since we have the third experimentally determined value, we can also determine this Kt from here, and if you have information about Kt, then we can also determine Kp. Okay, so generally, we don't really want to calculate it by ourselves how to determine each value. We are just introducing theoretically is possible. Okay, theoretically we can just vary this monomer concentration and initial concentration when you start the polymerization reaction, right? And we can also easily check the reaction rate and also the average degree of polymerization or the polymer chain length, right? So based on these experimentally determined values, we can determine Ki easily, but Kp and Kt separately determining them is not quite easy based on only these measurements. So by measuring this average lifetime, we can determine Kp and Kt separately too. Okay. The final part of free radical addition polymerization is molecular weight determination by distribution. Okay, remember from step growth polymerization, we also did molecular weight distribution. We derived the Cardos equation and also generalized Cardos equation, etc. Right? So we are going to do the similar things based on kind of similar approach. Okay. All right. Statistical treatment. So what we want to do is we want to determine the probability that an active species, here free radical, propagates rather than terminates. Okay, so there are basically two fates that this free radical can have, right? Free radical basically can attack monomers, basically doing the propagation, or they can just meet with another free radical and just die. Okay, so there are two fates that this free radical can have. All right, so let's just ignore initiation. Then this p-value is defined as the probability that free radical propagates rather than terminates. So since there are two fates, propagation and termination, this p-value, the probability, is just the rate of propagation over rate of propagation plus rate of termination, right? It's quite simple definition, right? It's kind of similar to p-value that we defined in step cross polymerization. The definition is different, right? It's kind of similar, but it's quite a little bit different, right? This P was the extent of reaction or the conversion, right? I mean, has somewhat similar meaning, but strictly it's a little bit different, right? So anyhow, we just first define this P as the probability that the free radical propagates rather than terminate, right? Okay. Then let's determine the probability of obtaining a chain of length n. Okay. So if you want to obtain a chain length of 1, okay, then this free radical should just die, right, without taking another monomer, right? Then we can get the polymer chain with length of 1, right? And if this free radical dies, the probability should be 1 minus p, right? 1 minus p, right? The probability that we can obtain the chain with the length of 1, okay? Similarly, if you want to obtain a polymer chain of 2, okay, then at first this free radical should propagate, okay, once, okay, propagate, basically react with another monomer, then just die, right? Then just die. Okay? By doing that, we can obtain the polymer chain of length 2. Okay? So the P2 is equal to P times 1 minus P. Okay? Okay? Since these two events basically occur separately, right, independent of occurrence, that's why we just multiply, right, as you have learned from like high school statistics, right? So by following similar approach, right, if you want to make a polymer chain with the length of n, what you do is you basically have to propagate n minus 1 times, right? N minus 1 times, and just that radical should die. Okay, so the probability that we obtain the polymer chain of length n by free radical addition polymerization is equal to p to n minus 1 times 1 minus p. Okay. Surprisingly, this result actually is same as the one that we obtained in step growth polymerization, right? Totally same result. Although the p-value, the definition is different, okay, but the result is same. Okay, so since we have already obtained the average number average and also weight average degree of polymerization in step growth polymerization as shown here, okay, the results are basically same even for free radical addition polymerization. Okay, so from this value we already know that PDI, polydispersity index, is 1 plus P, and if P approaches 1, this value basically approaches 2. Okay, very simple. Okay, but in this case we only consider the termination of disproportionation only. Okay, okay, we only consider this free radical just die. Okay, free radical just die without combination, right? They just die with basically having the same length of the free radical. Right? What if you consider the termination by combination? Okay, if termination is occurring by combination, then the resulting polymer chain length will be larger, right? Longer, right? So then the molecular weight distribution will be different, right? Okay, so here we will check the molecular weight distribution for termination by combination. Okay, So if the termination occurs by combination, so let's say that one polymer chain radical with the molecular length of I minus j basically terminates with another polymer chain radical with the polymer chain length of j, then we can basically form the polymer chains with the length of I, right? I minus j plus j, okay? But this is not radical, right? Just the dead polymer chains, okay? And if you want to calculate the probability of forming this I more dead chain by combination, okay, then this pi should be equal to the probability of forming this I minus j radical and also j radical, right? Pj and Pij. Okay, and the length of j could be varied, right? So we need to sum by the sigma from I to 1 to I minus 1. Okay, and since in previous slide we already calculated this Pj and Pij, Pj is equal to P to the j minus 1 times 1 minus P. Pi minus j is equal to Pi minus j minus 1 to 1 minus P. So if you just multiply these two values and put it here and just do the summation over this sigma, okay, that summation is given here, okay, and since there is no I variable here, j variable here, and we are doing the summation over j, right? So we can just simply multiply by I minus 1 here. Okay, the probability forming that chain with the polymer chain length of I is equal to I minus 1 times 1 minus p squared times p to the I minus 2. Okay, okay. So from this probability, we can calculate the number average degree of polymerization and also weight average degree of polymerization. Okay. So let's first calculate the number average molecular weight. So the number average molecular weight is basically equal to this probability of forming polymer chains with length I times just molecular weight of the I more, right? Basically, M is Mi. So if you put this probability here, okay, and the Mi is equal to I times M0, right? So if you do the calculation, right, this kind of calculation can be done by doing this. You remember this? If you take the derivative of the infinite series, right, you can easily get these expressions. Let's say that just you have this value already as shown here. Okay, so if you put these numbers in, the number average molecular weight, if the free radical polymerization occurs by termination by combination, okay, then the number average degree of polymerization is equal to 2 over 1 minus p, right? It's different, right? Okay, if the termination is by disproportionation, it was 1 over 1 minus p, right? Remember from previous slide here. Okay, okay, it's twice, right? The reason why is quite simple, right? Because it is occurring by combination, right? We are basically generating in average twice the molecular chain length by combination, right? That's why the number average degree of polymerization is 2 over 1 minus p. Similarly, you can also calculate the weight average molecular weight and also weight average degree of polymerization. If you do the calculation, you can easily get it is 2 plus p over 1 minus p. It's also different from the previous calculation, right? So from these two values, you can easily calculate PDI, not PI, PDI. PDI is equal to 2 plus p over 2. So if you take the this probability to 1, then the PDI value approaches 1.5. Okay, it's different, right? In its proportionation, it was 2, but in the combination case, it's 3/2. Okay. So up to here, we kind of finished the free radical addition polymerization. Okay. So I hope that you understand this clearly.